Hey everyone, thanks for coming. My name is Chung. I'm the CEO and co-founder of NCB. I happen to be one of the original co-authors of the Pandas library. So after I leave, I have to go catch a flight. After I leave, you can ask Sammy what he really thinks about Pandas. Okay. Cool. So we're going to go really deep down in the basement about building this new infrastructure and new tooling for multimodal data. So I want to convince you that it actually matters, right? So you see here, so this is the Burj Khalifa, right? You guys know this is the highest building, tallest building in the world. It's so tall that you can see it from like 60 miles away. That spire. It has the world's highest nightclub and the world's highest mosque. So it's Daft brings the party and 12 Labs brings the magic. But in order to build this high, you have to go really deep, right? The foundations are kind of crazy. This is like about 13 feet thick concrete slab that can support up to like 450,000 tons of building. But of course, the problem is, right, Dubai is in a desert and sand is super soft. So in addition to building that concrete slab, you need to have these like hanging piles that go all the way down like about 200 feet or 150 feet into the ground to stabilize the building. And that might be enough for other places, but Dubai is not just in a desert, it's also by the ocean. So at this depth, salty seawater comes in and starts to erode all of the metal piles that you've driven in. So what you have to do is actually run constantly electric current through the whole foundation so that you have a stable foundation that can live in sand, support the world's tallest building, and not get corroded over time. So remember, electric type is strong against water type. Okay, so so foundations are important, right? So if you don't have the right foundation, you don't end up with the Burj, you end up with the Leaning Tower of, well, this is actually wrong, Leaning Tower of San Francisco, Millennium Towers on Market Street, right? So this opened in 2009, it's been tilting and sinking ever since. Multiple, hundreds of millions of dollars in repairs. Today it's like, if you open the window at the wrong time, you get fined by the HOA like $10,000, right? It's ridiculous. Okay, so why do we care, right? Because foundations are important, and the foundation for multimodal AI is the data. And so if you don't have the right foundation, right, you end up with something like this. You'll notice that the star here is on the brightest point of reflection. That was absolutely on purpose. Okay, so why does AI need a new foundation? Well, data is much bigger, as you can kind of infer from Sammy's talk, right? So tabular data, if you look at TPCH workloads, 145 bytes per row. Embeddings, immediately you're at 25x per row. If you add images to that, 500x easily. If you're at videos, right, this is like crazy amount. Not only is each individual record much bigger, right? The data is also being generated at a much faster pace than before. So you're not limited by human input. This is automatically being generated at 1,000 tokens per second. And so what you end up with is something like training data for AI just increases in size by like 3 orders of magnitude every few years, right? So CFAR is like 163 megabytes, right? This is kind of like when I was working on pandas. This is the size of data you load into a pandas data frame pretty easily. You can get up to like a couple of gigabytes. ImageNet, 150 gigabytes, like your typical language or text-only LLM models, like terabyte scale, right? And image video models are easily petabyte or tens of petabytes of scale. Right? So not only is scale much bigger, so the data has to change, the tooling has to be distributed, but also the cost model for working with AI datasets also need to change. Right? So if you're at like big data, for example, you're being charged by the number of gigabytes scanned, right? So if you're here, you get charged by like this is the pricing where BigQuery set, and now you're at this scale, and that's just crazy. Okay. Second reason is not just the data's changed, but workloads are very diverse, more diverse than tabular data. So it's not just OLAP and analytics, but search, vector search, full text search, training, exploration, curation, evaluation, the works. So in order to satisfy all these different workloads, you need a new sort of data foundation that can satisfy all of these with high performance and low cost. So if you take one distributed training example, so it's filter, shuffle, distribute, typical training workflow, So first is you need to be able to filter your large amount of data on like metadata dimensions or something like that to get to the right subset. That required a fast scan of your metadata dimensions. And then you need to do shuffle, which requires fast random access. So you can get to the right rows throughout your big data set. And then you distribute the row IDs to the different workers. And then you need to be able to efficiently stream the right blobs, the images, and tensors, and videos into each worker. So when you put all that together, so remember, this is one workload that requires all three of these. And unfortunately, if you look at Parquet, if you look at, I don't know, like a web data set or whatnot, none of those things can satisfy all three of them. So that means you're sacrificing one or two parts of your workflow by using one of these existing foundations, And so, I've sort of called this the new CAP theorem for AI. It's joking because the CAP theorem is unsolvable. This new CAP theorem of AI data is actually solvable, and this is why we made Lance format. And so if you're not building off of something that's new, if you're building off of existing foundation for tabular data, but you're using it for multimodal data, you end up with this sort of Rube Goldberg system where folks at various AI or large enterprise tech companies have come up as the solution for managing all of their data from the data at rest to like search to in a vector database to training, evaluation, and all of that. So you have single purpose data warehouses, different copies, different compute for each of these. And so I posit that this is not a solution slide, this is a problem slide. And so how do we solve that? So the reason why we invented Lance was, so this makes managing AI data too expensive, really complicated. And what's probably worse is that the most expensive hires in your organization are just like spending all their time dealing with, why isn't my integer being saved? Or, how do I work with multimodal data effectively and get good performance and good VDFs? And so so this is sort of the motivation behind us in trying to build Lance format, which is we ask that question, like, what if we could have it all, as opposed to forcing you to pick and choose. And so, call Lance CB, call it not your grandma's data lake, and it is a developer-friendly and open source new storage format for your data lake for multimodal data. It is like Daft, relies heavily on Apache Arrow, and we're built in Rust, and so there's a lot of compatibility there. We make it available in Python, TypeScript, and then also JavaScript, Java SDKs as well. And it's great for storing all different kinds of multimodal data, plus embeddings and enabling hyperscale search and computations and training. All right, so let's talk about the foundations on all of that, which is Lance columnar format. Right, so we're trying to solve this problem from the ground up and meet Daft in the middle. And so Lance columnar format is sort of 3-in-1 package. There's a file format, there's a table format, and there's an indexing subsystem. So the file format is basically trying to solve the problem of whatever compute engine I use at the higher level, I want to access my data really, really fast. Right? So Lance is columnar, so scans are on par with Parquet. we use advanced encodings for really fast random access, around 100 to 1,000 times faster than Parquet. And then put in lots of optimizations for managing large blob data, meaning your images and your video data. So we got rid of row groups from Parquet. We made the layout prefetch friendly. And then we also optimize it for both local NVMe storage for fast caching, and then also object store for very efficient large scale storage. So basically, it's whether it's scans and random access and whatever data type it is, you can get your data really, really fast. And that's what the file format is. The table format solves the problem of, okay, I now have 10 petabytes of data sitting in object store in an immutable data format. I want to add a column to run a new experiment, right? How do I do that without copying 10 petabytes of data? And that's what the table format is for. So basically, that allows us to do versioning, schema evolution, and then present that Apache Arrow API. So versioning basically solves the problem of how do I reproduce that model, right? Like I run the model, I can version the code, I can go back to that exact code that I ran on Ray or on Daft to create that model. But how do I save the data? Right? And so Lance, with the table format, Lance allows you to have a version number that automatically gets generated as you update the data, and then you can associate Lance data version with a job ID from whatever that compute. And those two things plus the code allows you to exactly reproduce the model. The schema evolution is basically what allows you to say, please stop using web data set. If I want to add a column to 10 petabytes of data, I don't need to copy 10 petabytes and then update that data and put it back. I can just add new files with that new column. And then the Arrow API is basically allowing Lance to almost work with everything out of the box, as Arrow's now sort of that in-memory format standard, right? The last part is indexing, and that indexing solves the problem of search, right? You have 10 petabytes of images. You want to ask a question, where are the images of stock cars with annotated problems in San Francisco? My co-founder worked at Cruise, so these questions tend to come from autonomous vehicles. And so to help answer that question, right, we've added 3 types of indexing with lots of additional ones to come. So scalar indexing allows you to do sort of question the smaller primitive columns. So for example, in San Francisco, vector index allows you to do large scale similarity search, and then full text search allows you to just do keywords or fuzzy search, and all these work off of object store and does not require you to hold everything in memory, right? So with indexing, we allow you to do filtered and hybrid search at billion scale directly from the object store. So when you put all these 3 things together, this is actually how they can take advantage of each other. So for example, the indexing doesn't work without fast random access, right? The index tells you which rows to look in your data set, but if you don't have fast random access, you can't get to it fast. The schema evolution for multimodal data won't work properly without large blob optimizations. Like if you add a new column and compaction takes a long time, you're not going to have a great experience. And then the I/O execution optimizations for random access also depends on having a format that actually gives you fast random access. So I'll try to speed through some of this rest of the content here. The catch is basically disk size. So by default, in order to give you good scans and good random access, we can't do block and file compression. Instead, we rely on encodings. So if you were paying attention to SAMI, you know that with JPEGs, their encoding and the compression happens at the record level. So it doesn't really matter. It's really for just the scalar data types, right? So available today in Lance is dictionary, FSST, bit packing, hack struct encodings that compress dictionary data, string data, things like that. Time series and other sort of better blocks type of encodings are on the road. And one of the most exciting things about Lance is that encodings are very extensible. It's very much easier to add an encoding to Lance than Parquet. And then, yeah, so at the end of the day, sort of this is what Lance format gives you. You have all of your data in one place, unified storage, and then you can have different types of queries, right? Because it's not just the data that can be multimodal. The workloads and the queries can be multimodal as well, from analytics to training to search and retrieval. All right, so Lance works with all of your sort of small and large data tools. But as an example, let's take a look at my favorite Spark killer here. And so thanks to, I think Jay knocked this out in like half an hour or something. And like basically you can read and write Lance data from Daft. And then you can add filters on that. And so this is one of the things where we're hoping to push in for the rest of the year, New Year's, deepen these query engine integrations to do push down. So here you can do .where with this filter condition. With the Lance data set, if you can actually push this filter down if the lat column is indexed. And so you can get much faster performance than reading the whole column into memory first. And so there's also array integration. So you can do stuff like large scale schema evolution automatically from this array integration. And you can also do very large scale index training, like vector index training in a distributed fashion. And we run that with on LandCB. All right, so thank you for listening to me ramble. We'd love to have you in our community Discord, and yeah, give us a shout. Contact at landcb.com if you want more information on hosted LandCB.